Welcome, this is Coach Dorf. Let's continue our discussion about derivatives and rates of change. So when I watch a movie or a series on Netflix has several episodes, they'll often start an episode with a recap of what's been done on previous episodes. Let's do the same thing here. What have we already learned about derivatives? Well, first of all, we have the definition of a derivative at a point, at the point x equals a. Okay, and what was that definition here? That was could be thought of first as the derivative of f of a is going to be the limit as h goes to 0 of f of a plus h minus f of a all over h. Or we could also think of the derivative as the limit as x goes to a of f of x minus f of a all over x minus a. And an example of this, of doing this, was following. So let my function f of x equal 1 over x find the derivative at 2. So when I do that, I'll use definition letter B here, the second definition. Okay, so the derivative at 2 is going to equal the limit as x goes to 2 of f of x minus f of 2 over x minus 2. So that's going to be the limit as x goes to 2 of 1 over x minus 1/2 all over x minus 2. And then we get the limit as x goes to 2. Oh, before I do that, the first thing I would do now is I would do direct substitution. When I put in x equals 2 here in the numerator, I get a 1/2 minus 1/2, which is 0. Denominator, I get 2 minus 2, which is 0. So I get 0 over 0, which is an indeterminate form. It means that we don't know what the answer is yet, and we have to do more work. So what more work do I need to do? Well, I look at my numerator, and I have a fraction minus a fraction, so I want to combine those together. And in long term, what I should be thinking in this problem is that because we have x going to 2 here, I should be able to get an x minus 2 in the denominator and x minus 2 in the numerator, and those will cancel each other out. The reason, because I have that x minus 2 in the top and the x minus 2 in the bottom, that's why I get the 0 over 0. All right, so I'm looking for a representation of the top where I'm going to have an x minus 2 there times some other quantity. All right, and I'm going to find that by simplifying the numerator. All right, so how do I simplify that numerator? Well, we've got an x in this denominator here and a 2 in the denominator here. So I'm going to let my common denominator be 2x. And I ask myself, what do I need to multiply 1 over x to get a 2x in the denominator? Well, that's going to be, I'm going to multiply it by 2 over 2. So I should have a 2 over 2x in the first one. And then what do I need to multiply my second fraction on the top, that 1 over 2 by, to get a 2x in the denominator? That's going to be an x over an x. And so in the second fraction, I'm going to have an x over 2x. And I'm going to rewrite my x minus 2 in the whole denominator there. All right, so then again, I have the limit as x is going to 2. Now I'm going to combine what I have in the top, the blue fractions there, to make one fraction. When I do that, I have 2 minus x all over 2x, and then that's all over x minus 2. All right, so now I have a fraction on the top, and I have an x minus 2 in the bottom. And I can think, though, of that denominator, that x minus 2, as really a fraction, because that's the same thing as x minus 2 over 1. And when I have a fraction over a fraction, that's the same thing as a fraction divided by a fraction. And I can divide fractions by taking the first fraction, writing it down, and then multiplying by the reciprocal of the second fraction. So let's do that. So I have x minus 2 here. Then I've got the first fraction, the top fraction, 2 minus x over 2x. And now I'm going to multiply by the reciprocal of the denominator fraction, which is that x minus 1 over that x minus 2 all over 1. If I take the reciprocal of that, that's 1 over x minus 2, and I have this. All right, now I look at this, and I say that I can think of this as I have just a 2 minus x in the top, and in the denominator, I have 2x times x minus 2. I don't have my x minus 2 in the top, or at least it doesn't look right like that I have that right now. But we note, so notice here that 2 minus x, I could write that as minus x plus 2 by just switching the order there, it doesn't matter. And now I could take out a negative 1 there. When I take out a negative 1 from negative x, that gives me an x. And if I take out a negative 1 from a positive 2, that's going to give me a minus 2. And I can check that that's correct, because if I multiply negative 1 by x, I get a negative x. And then if I multiply a negative 1 by a negative 2, I get a positive 2. So this is correct. All right, so I'll use that fact then to rewrite my limit, to rewrite the top part to give me a negative 1 times x minus 2 on the top, okay, times a 1 that I had up there. And on the denominator, I've got the 2x and I've got the x minus 2. Now I've got my x minus 2 on both the top and the bottom. I can cancel those out, and I can then rewrite this as the limit as x goes to 2 of negative 1 over 2x. And I can, since I've canceled out my x minus 2, I'll do my direct substitution again. When I do that, I'm plugging in x equals 2. I get a negative 1 over 2 times 2, which is negative 1/4. And that's my answer. So the derivative at 2 is negative 1/4. Okay, so that's the first thing that we talked about when we did the direct definition of derivatives, or we're talking about derivatives. We did this definition of the derivative at a point. The second thing we talked about is what's the meaning of derivatives. Well, one of the meanings of derivative is that it equals the slope of the tangent line. And specifically, what do we mean by that, slope of the tangent line? That means that if I have my function represented as a graph, then I can take that point that I'm looking at, and I look at the graph there, and I draw the tangent line to it, and like, let me just show you that in terms of actually of a graph. So let's suppose this is my graph of my function y equals f of x, and I take a point on there. Okay, there's my point x equals a. And I can look at the tangent line. The tangent line intersects the blue curve at one point, and the derivative, so f prime at a is going to equal the slope of this tangent line there. All right. To give you an example of how this is sometimes seen in problems, they can give you the graph of a function. Let's suppose here's my graph of my function. I'm going to go like this, and then I'm going to go like this, and then it's going to go like that. There's my function y equals f of x, and I'm going to draw some things in here. This is going to be the point 1. This will be the point 2, 3. This is my x-axis, my y-axis, and we'll call this point -1, this point -2. Okay, what is the graph of the derivative? Let's go over here. So now on the right side, I'm going to draw the graph of the derivative. Well, using the idea that the derivative equals the slope of the tangent line, I'm going to look at my blue curve, I'm going to take some points on it, and I'm going to draw the tangent line and look at their slopes. The easiest ones to start with are the ones that have these curves that when I draw the tangent line is flat or horizontal. So that happens about here, which we'll say is x equals -2. If I draw the tangent line there, the slope of that is 0. So if I go over to my graph of my derivative, draw in some points here, some x values. So those are x's, and again, here's my y-axis, which is the derivative. What do I notice? I notice that on my blue line, when I drew the tangent line at x equals -2, I got a flat line, which means the slope was 0. That means for the graph of my derivative, I should have that point x equals -2 and y equals 0, because the slope is 0. Likewise, if I go on my blue line and I draw the tangent line at x equals 1, the slope of that is also 0. Okay, so on my graph of my derivative, I should have a 0 there. Now, if I take a point where on my blue line where x is less than -2, take this, draw a tangent line there. What's the slope of that look like? Well, I don't know the exact value, but I know that that's a positive slope because it's going up. So that means if I go back to my graph of my derivative, the slope value is positive. So it means I have to be above the x-axis. So the graph of my derivative should be above the x-axis when x is less than -2. If I go back to my blue line, if I take a point, let's say I take a point between -2 and 1, draw the tangent line there, the slope of that is negative. It's going downhill. And so likewise, for any of the points then between -2 and 1 on the graph of my derivative, it should be below the x-axis. It should be a negative number. So it should be down here. And I know it has to connect up at with the point we have at x equals 1 and y equals 0. So I connect it right there. And then finally, if I take a point on my blue graph where it's larger than 1, take a point there, draw the tangent line, okay? I don't know the exact value, but I know that that's going to be a positive value. And so when I go over to the graph of the derivative, it should be above the x-axis. And that's a sketch of what the graph of the derivative would look like for the blue function that I was given there. So again, one of the meanings of derivatives is that it's the slope of the tangent line. And that's usually what students think of it most of all. But we can also think of the derivative as rate of change. And this often comes about when we have a description of our function. So not necessarily that we have the graph. In the previous example, where we thought of the derivative as the slope of the tangent line, that often works well if we have the graph of a function. But if I have a function that's given as a description, then I can think of the derivative as a rate of change. All right. So for example, suppose, do an example here. Let C of t equal the percentage of full capacity of the battery in a cell phone. All right. So what are some, so T would represent T equals time. We'll just say maybe in hours, we think of that. So it could be like at 0 hours, my cell phone percentage is at 10%. What happens as if I plug it in and I increase it with time? Well, if I'm charging it, then after 1 hour, that percentage is going to go from 10% to a larger number. After 2 hours, it's going to get larger. The percentage is going to be larger, and it's going to keep increasing until I get to about 100%. It's not going to go above 100%. You can't charge it to be something larger than 100%, but you can charge it to up to 100%. So if I were to make a graph of that, where this represented time on the one axis, and this is percentage charged, and again, I'm looking at charging it over time. Okay. The graph might look something like this. I plug my cell phone in, I'm charging it. It may start off at a low value here, okay? And over time, it's going to be increasing, and it's going to get closer to 100%, where this is equal to 100% there, okay? What does the derivative represent? Well, the derivative of C again represents the percentage of the full capacity of the battery charged. Okay, so right here. Then what's that going to represent? Well, that's going to equal the rate of change of the percentage of full capacity. If I want to think of that in terms of a graph, what's that going to mean again? I put some values in here. So how much is it going to be changing through time? Well, when I first plug it in, it's going to be charging really quickly. And so the value is going to be higher up here. But it's going to be, the rate of change is going to decrease with time. And as the time increases and the charge gets closer to 100%, the rate of change is going to be less and less. And it's going to look something like this. So the idea again here is if I have a description of a function, then the derivative is going to be the rate of change of that description there. Okay. And the third way that we've talked about the derivative is the derivative could equal velocity or speed if my function is representing like distance or position. So like if I were to have a table of a function represented by table and f give me the position values, then the derivative would represent then the speed or velocity of that. Okay, that's a recap of things that we have talked about so far. So what's new? So new ideas here. Well, as we just mentioned, we talked about the derivative of a function at a point. Well, we could change this derivative so it doesn't have to be just at a particular point, but it could be the derivative for any value in the domain of the function. And this is what we're going to get. We're going to get the definition of the derivative of a function of f. And we're going to write that to be the derivative of f of x equals the limit as h goes to 0 of f of x plus h minus f of x over h. Now you may say, well, wait a minute, this doesn't look like anything new. Well, all we've done is you're right, we have just taken the definition of the derivative of a function at a point, x equals a, and we replaced that a with the x. So this is very similar to the definition of the derivative that we had before. But before we were talking about the definition of the derivative at a point. Now we're talking about it at any x value. And this then gives us the derivative as a function, and that is very, very helpful. Okay, it may not be apparent yet, but it is very, very helpful. And this is what we will be using for the remainder of the course. Also, this gives us a more general way to look at what we were doing previously. So let me give you an example here of doing this. All right, let's suppose we're going to, again, we'll do the same type of idea. I'm going to do let f of x equal 1 over x. But now we're going to find the derivative in general. All right, so we're going to use the definition f prime of x equals the limit as h goes to 0 of f of x plus h minus f of x all over h. So that's the limit as h goes to 0 of 1 over x plus h minus 1 over x all over h. I do direct substitution here. I put in h equals 0. I get 1 over x minus 1 over x in the numerator. That's 0. And I get h equals 0 in the denominator. So I get 0 over 0 indeterminate form. Not a big surprise. You probably should be expecting that. Okay, so I need to find a way. I need to do more work. I need to find a way to simplify this or to rewrite this. And the way to do that is to simplify or combine the fractions that are in the numerator. All right, so I have to get a common denominator or what's in the numerator, and that common denominator is going to be x times parentheses x plus h close parentheses. So I'm going to have x plus h in my denominator here, and x times x plus h here. And how do I do that? Well, I need to multiply the first fraction in the numerator by x on the top and x on the bottom. And so I'm going to get an x up there. And in the second fraction here, I need to multiply the denominator by x plus h. So I need to multiply the top by that same amount. And I'm going to have x plus h there. And that's, again, all over h. And so now I've got two fractions in the numerator. So I'm going to combine them and rewrite that as one fraction in the numerator. And I get x minus parentheses x plus h all over x times x plus h. And that's all over h. Notice that I used a parentheses when I combine those. I put a parentheses here because this negative I have here gets distributed to everything. And so by doing that parentheses, I represent that I'm doing that. Okay, so now if I get rid of that parentheses, I'm going to have an x minus h. Again, notice you should have a minus there, not a plus. That's a common mistake that students sometimes make. All right, and then I have my denominator, and then that whole denominator is h there. Okay, so now I can cancel out these x's there, and that's going to now give me my limit as h goes to 0 of negative h over x times x plus h all over my big H. And I have a fraction in the numerator, and I have that h in the bottom, but I can think of that as a fraction in the denominator. And so I have the limit as h goes to 0. And because I have a fraction over a fraction, I can rewrite that as a multiplication problem, because a fraction over a fraction is a fraction divided by a fraction. So I'll write that as the first fraction here, and I'll multiply by the reciprocal of the second fraction, which is this. All right, and then I can see I can cancel out the h's here. And when I do that, then I've got the limit as h goes to 0. I have a negative 1 on top, and I have an x times parentheses x plus h in the denominator. And notice I should expect that I would cancel out the h on the top and the bottom that we just did, because we have this limit as h goes to 0, and that means I should have an h minus 0 or an h on the top and the bottom. That's what's caused the 0 over 0. That gave me the indeterminate form at the very beginning. All right, so now I have this, and now I do my direct substitution, and I get negative 1, and I get x in the denominator times x plus 0, which then simplifies to be negative 1 over x squared. Now, how is this different than what we did at the example we did at the very beginning? Okay, so recall we did the derivative at 2, and we came up with negative 1 over 4. Well, here we have the derivative of x is negative 1 over x squared. So we could go ahead and take what we just did and put in x equals 2. If we let x equal 2, then we have here the same thing. So I'm using this right here. And then my answer, though, here is the same as this. Same. But what's nice now about my function is we could let f be other things. We could say, what is f prime of 3? Well, I don't have to now redo the whole problem. I can just put in 3 here, and I get negative 1/9. Or I could do the derivative at 1, and then I get negative 1 squared, which is then negative 1. Okay, and I can keep doing that. I can find it for everything. So this new definition here, or this definition of the derivative of the function f of x as a function, allows me to find all the answers I need instead of just finding it at one particular point like we were doing previously. Okay. One other part here too is that I could use my previous definition. So we could use the previous definition that we called B at the very beginning of this presentation, that the derivative of A is going to be the limit as x goes to A of f of x minus f of A all over x minus A. So you could do this, and then how do you find f prime of x? Then to find f prime of x, we substitute x equaling A into f prime of A. Okay. So how is this a little different than what we have been doing when we're finding the derivative at a point? Well, here we're not putting in a particular number for A. We're not saying find f prime of 2, but instead we're saying let's find f prime of the letter A. And then we do that. And then when we finally get done with it, we then substitute in x for all the A's there, and we get the same general definition of derivative f prime of x. Okay, so now some people say, will ask, why definitions? Why is it important that we know these definitions? And that's a good question. Why should we know these things? Because if you've had calculus before, or even if you haven't, you might know that we're going to have some shortcuts. Our next discussions, we'll talk about some quicker ways to find derivatives. We'll talk about a thing called the power rule that'll allow us to find the derivative. So just give you a preview here. Power rule, find derivative of things of f of x equal x to the fourth. We'll find a shortcut for that. Then we'll have like the product rule, which will be a shortcut to finding the derivative when I have two things multiplied together. We'll also have the quotient rule. And we'll have the chain rule. And all these are all shortcuts to finding derivatives. And so students will say, well, why didn't we just start with the shortcuts and skip the derivatives? Because the shortcuts make it easier to find them. Well, it is true that they make it easier. So why do we have definitions? Why definitions? Well, first of all, how did they come up with these shortcuts? Okay, shortcuts are possible because we use the definition. Someone figured them out by using definitions. Okay, there was no book. And somebody said, oh yeah, here's the definitions of derivatives. Oh, look, here's a book. And wow, here are all these shortcuts. No, there was no book with those shortcuts. How did they get those shortcuts? Like, how did they get the power rule? How did they get the quotient rule? People used the definitions, and then they were able to create the shortcuts by using the definitions. So the shortcuts exist because of the definitions. That's one reason why the definitions are important. The second is some functions for some functions have no shortcuts. All right. For example, suppose I have the function f of x equals x squared over absolute value of x. Well, now there is a shortcut for just x squared, and there is a shortcut if I have a rational function, so like a fraction like I have here. There's a shortcut for that too, but there's not one when I have absolute value of x. Okay, how do we find the derivative? We have to use the definition or the idea of the definition. figure that out. Okay, what's another example? Sometimes a function can be represented as a table of data. All right, so I'm a diabetic, and let me show you right here. I have a thing called a continuous glucometer, and what that means is I have this little device that's put in my arm here. You can kind of even see it right there. And it's a little transistor, and it measures my blood sugar every 5 minutes. And it sends that data to my cell phone. And here, I'll show you a little bit on my cell phone. Hopefully you can see this. So you can see both a number up here, and you can see a graph down here. There's the data. Now, on that number there, it says that my blood sugar is 92, which is a really good number. It's pretty normal. It's probably what your blood sugar is. That arrow there represents the derivative. It means it's pointing straight across. It means that I have a flat derivative, that my function is pretty flat. And if you look at my graph there, right over here, okay, on the far right side there, the little dots there representing the function, it's not changing much. The derivative there would be flat. There's no shortcut to figure out what that derivative is there. We have to use the definition of the derivative. But they're using that in medical devices like this continuous glucometer, it's CGM, to figure out what the derivative of this is. Now, the doctors and the medical devices won't call it the derivative, but that's what it is. It's showing me that my blood sugar levels are flat, okay? That the derivative there is 0, which is really good. That's what I want. If my blood sugars are increasing, they'll have the arrow will be pointing up, and that means the derivative is positive. If my blood sugars are going down, then I'll have that arrow pointing down, and that means my derivative of my blood sugars is negative. All right, we can only figure those out by using the definition of the derivative or the idea of the definition of the derivative. Okay, and then finally, a fun fact is that you can use, knowing the definition of the derivative, allows people to apply the idea to new settings. Okay, and that's kind of what I was talking about with this CGM here, this continuous glucometer for my blood sugars, but it also happens in the case when we're dealing with artificial intelligence and machine learning. The idea that's used there to use that data science, that artificial intelligence and the machine learning to teach a machine or a software or a program to learn something, to be able to evaluate it and to diagnose what's happening there, they're using derivatives in there. All right. The fact that the people who worked on this understood what the idea of derivatives were allowed them then to actually make this thing possible. So those are some reasons why the definitions are important. Given that, though, I'm sure a lot of you will be really happy as we move forward that we're now going to be then talking more about these shortcuts. And the shortcuts aren't bad, they're good, but just to remember that there's an importance, there's a reason why we have these definitions and why we need to use them. All right, so what's new then besides this new definition of the derivative, or this definition of the derivative as a function? There's some alternate notation that are used for derivatives. And this is important because sometimes when you're in a different field or a different discipline, they might use a different way to represent or to designate the derivative. So we've talked about f prime of x, that's one notation. Sometimes we will talk about y prime. Since f of x is often equal to y, we can talk about the derivative as being y prime. Another way that we'll talk about it is to represent it as dy dx. So we're taking the derivative of y with respect to x. Another way that you will see in other disciplines is d dx of f of x. And we will talk a little bit about that. And then a final way that I've seen it sometimes is that capital D sub x of f of x. All of these, okay, all of these represent the derivative. Okay, I'm getting that low battery signal on my iPad here, so hopefully I can finish this before we get done, or my battery runs out. Okay, so we have these alternate definitions of, or notations for derivative. There are times when is a function not differentiable at a point. Well, there are three main cases, and that is at a corner. So if I have a graph of a function, let's say we do this function here. So this is my function here is absolute value of x. The function f is not differentiable at x equals 0 here, because I have a corner there. That is a corner there. It's a point. Okay. And if you think about this in terms of what does one of the meanings of the derivatives, if I have a graph of a function, the derivative represents the slope of the tangent line. If I tried to draw the tangent line in here, what would be the tangent line at that point? Is that the tangent line? Or is that the tangent line? Or is that the tangent line? Which one is the tangent line? We don't know, because all of those could possibly be the tangent line. So at a corner, the function doesn't have a derivative at that corner there. A second case where the function is not derivative, if there is a discontinuity. And this is one reason why we talked about continuity earlier. If I draw a graph of this, it could be something like this. All right. What's a function that represents that? If I have f of x equals 1, if x is greater than 0, and -1 if x is less than 0. Oh, sorry, write that there. If x is less than 0, then this is not differentiable at x equals 0. Okay, there's discontinuity there. In fact, even if I just fill one of these in, let's just fill this one in there, I still can't find the derivative there. Okay, and the third case where a function is not differentiable is at a vertical asymptote. Now we've talked about horizontal asymptotes, or sorry, not vertical asymptote. Let me erase this. A vertical tangent. Okay, what does a vertical tangent look like? That's like this function here. That looks like this, like that. Okay, and a function that represents that is this one right here, x equaling 1/3. This here is a vertical tangent at x equals 0. So this is not differentiable at x equals 0. Okay, those are three cases where a function is not differentiable. Some results here, call these theorems. One important theorem is that if f is differentiable at the point x or point A, then f is also continuous at A. I'm not going to prove this here in this discussion, but you can find it in the book and lots of other sources. Okay, so here's a question. If f is continuous at A, is f differentiable at A? Okay, so if it's continuous at a point, is it differentiable at that point? Well, the answer is no. And an example of this is f of x equal the absolute value of x. Okay, we had just talked about that a little bit ago. The graph of that looks like that. And that's not differentiable at x equals 0, but is continuous at, well, for negative infinity to infinity. All right. And that makes sense, just because if A is true, then B is true, doesn't mean that if B is true, A is also true. For a good example would be if it is snowing outside, then it's cold. It's not the same thing to say that if it's cold, it has to be snowing. Okay. All right. Then let's see, what's some final things that we have here. We can do higher level of derivatives. Okay, so we can do this. This is called the first derivative. That's what we've been talking about. But in many cases, if I have a first derivative, I can also take a second derivative. So this is a derivative of the derivative. And I could do a third derivative or a fourth derivative. I can just keep doing derivatives. All right. So we found earlier, just give you an example. Okay, earlier we showed that if f of x equals 1 over x, then the derivative was negative 1 over x squared. We can compute the derivative of f prime of x equaling this to be f double prime of x, and that was going to equal then 2 over x cubed. And we could also take the derivative of this of f prime. So we could take the derivative of the second derivative to get the third derivative, and we would get the third derivative of x would equal negative 6 over x to the fourth. Okay, now you may be wondering how we do this. We will talk more about that next time when we do the power rule. Okay, so what's important here is not the results that I got here, but the fact that if I have a function of derivative, sometimes I can take the derivative of that derivative and I get a thing called the second derivative. And I can take the derivative of the second derivative and get the third derivative and so forth, just like that. Okay, now that we've talked about first derivatives, second derivatives, and other derivatives, let's look at an example of a problem that we could do. All right, so here we have the graph of a function, its first derivative, and its graph of its second derivative. And we don't know which is which, but we need to determine which of these lines, the A, B, and C, the blue, red, and green one, are the function, the first derivative, and the second derivative. What I would do in this problem is I would look at where there are valleys and hills. So let's start with letter A here. Okay, so letter A is the blue graph. And as I look at it, where does it have a valley and a hill? Well, there is a valley right here at this point in purple here. And at that point, I'm going to have my tangent line is going to be horizontal or flat. It's the graph of its derivative then should intersect the x-axis right above that point. So right above that point is up here, but there is no curve that intersects it there. So this suggests to me that B and C are not graphs of the derivative of A, either one of those. So that probably means that A is going to be the graph of the second derivative. Let's look at B. So let me take a different color here. I'm going to take orange here. So graph of B, where does it have a valley and a hill? Well, it has right at this point here, if I draw the slope of the tangent line in orange there, that's where the derivative is, the slope of the tangent line is 0, so the derivative should be 0. That matches up with where the green line crosses. Let's look at again, another point on the red curve. Right here in orange, we have the graph of the tangent line there above x equals -1 is also has a horizontal tangent line. And if I go straight down, I see right here, that's where the green line crosses the x-axis. All right, so that suggests that if I have B, that B is going to, the graph of B is, that's going to be my function, then C is going to equal the graph of the derivative of B. And we can check this further by looking at some more tangent lines of B. So if I take a point here, like at about -6, draw the slope of the tangent line, it's that slope of that line is negative. And that corresponds with the green line being below the x-axis. Being below the x-axis means that the C values are negative, and that's what I get for the slope of the tangent line for the red line. If I go to a point about, let's say, -2 or so, draw the tangent line there on B, the red graph, and I look at that, I have a positive slope, and that matches with the green line being above the x-axis, positive values. And finally, if I take a point where x is +1 on the red line, I draw the tangent, slope of that is negative, and I see that the green line is below the x-axis. So yeah, so C is the graph of the derivative of B. Now let's look at C. Okay, if I take the graph of C here, where does it have valleys and hills? Well, right here at about -2.5, there is a hill. And if I draw on the graph of C, and if I draw the tangent line in this darker green here, that slope is 0. There should be a curve that crosses the x-axis there, and that is the blue line. So that's going to suggest that C is going to, I mean, that A is going to be the graph of the derivative of C. Check this out a little bit further. So I continue on the graph C. I also notice that at about x equals 2, around 2, if I draw the tangent line there, it's horizontal, and that means above it here, we should have a place where the blue line crosses the x-axis, and it does. And I can continue my discussion along this line. So given that data here, I would say then that that B equals the graph of F, C equals the graph of F prime, and A equals the graph of the derivative of F prime, which is F double prime. And that's my answer. Thanks. Hope you have a great day.